things evaporate quickly because what do you think? How many people think they have high intermolecular bonds? How many people think they have low intermolecular bonds? That would be right. Things evaporate because they aren't bonded together. They're like, I'm out of here. Okay? So volatility of a gas. So the more volatile the liquid, okay, because this is going from a liquid to a gas, then the easier it goes into its gas phase from a liquid. So I have a couple of slides to consider relative volatilities. So you know how I like to draw beakers. I'll try to be neater. There's my beaker. Okay. I'm going to put a liquid in there, and I'm going to cover it. I'm going to seal it. Doesn't look like it's sealed. Call that liquid A. Okay, and this is going to be my liquid B. I'm going to seal it. I'm going to allow enough time for, in both of those cases, I'll call this B, both of those cases, that headspace above the liquid, okay, this is liquid, this is liquid, this is gas, this is gas. I'm going to allow it to become saturated. Saturated means it's in dynamic equilibrium. Those gas particles are going to stay there. So this is saying, this is different than the next slide. This says it is at the same temperature. So T is equal to same. Okay. So I'm going to go ahead and in the B, I'm going to go ahead and put more dots. Based upon that kind of silliness, which one has the higher equilibrium vapor pressure? B, exactly. So this has a higher EVP, equilibrium vapor pressure. And this is what we say generally more volatile. That's M-O-R-E, volatile. Okay? Makes sense. So let's change it up a little bit. On the next slide, it says you have two solutions, A and B, and so I'll go ahead and draw them down here. But if you read it, it says your goal is to go ahead and to get them at the same equilibrium vapor pressure. So here's my A, liquid, watch glass, gases, given enough time. And here is my B, liquid, watch glass, gases, give it time. And in this case, I'm going to try to make the number of particles the same. Okay, but they are different substances. They have different relative volatilities. Let's say A and B are the same as they were before. Okay, B was more volatile before. So honestly, does this make sense? In order to have the same equilibrium vapor pressure, what do I got to do to this temperature? How many people think I raise it? How many people think I lower it? Me too. Very good. Does that make sense? Good job. So in order to pull this off, I would need to lower temperature because it's more volatile. Yeah, well, that's kind of relative volatility. And it's definitely an indication of those intermolecular bonds. So in this part, pretty soon, okay, I think it's still in this part, we're going to come up with phase diagrams. So what are the three physical phases? Not including plasma. People want to keep putting plasma in there. What are three physical phases? Yeah, solid, liquid, and gas, exactly. So in the phase diagrams, we're going to have solid too, but this is only the liquid gas phase diagram part of it. So the way you read this, okay, I'll go ahead and, my drawings are going to go away here in a minute, but everything that is kind of up and above, okay, that is a liquid, okay, and anything that is below those lines, kind of below and kind of to the right, that is a gas, that substance. There are different colored lines. You see 5 lines. Each line represents a different compound. So let's pick on, first. Then I revealed what we have along the X and the Y axis. It's very important. Start to kind of get your wits about you. Along the x-axis, we have temperature, so we're increasing temperature. And I said that this was a gas, didn't I? Kind of down and below. Okay, increasing temperature, that makes sense, okay? And then here, we're increasing pressure, okay? And I said, actually, that's starting to favor a liquid. And I don't know if you remember, but actually in Chem 1, we just barely touched on this. That gases behave more like a liquid the more pressure you get them at the lower temperatures. And so actually, we've transitioned when we jump that line from a gas to a liquid, basically. Okay, so the black line is water. So in other words, the way this works is if we pick on water, you guys would tell me that there's water in this room, right? That's not entirely dry room. And let's just say we're running, let's say we're running about 25 Celsius or so. Okay, so what you do is you go up on the black line, it's kind of messy there, but then you go over and you say if this air were saturated, we'd be running, I don't know, what do you think that line is in millimeters of mercury? 30, yeah. Sounds good, about 30 millimeters of mercury. That's when we're right at the dew-point temperature, basically, of this room would be saturated with water vapor at that temperature. That's how that works. Okay, so the black line is water. The red line is diethyl ether. Oh, okay. Let's talk polarity here. So the cute little structure of diethyl ether is there. What do you think? I'll just kind of ramble out loud. Remember the CH3 and the CH2s those are kind of like we saw in the alkanes. Those are basically a carbon with hydrogen sticking out from them. The oxygen would bring a little bit of polarity, wouldn't it? It kind of breaks out of the alkane mode. Okay, so there's a little bit of polarity there. Then that would be this red line here. If we compare diethyl ether to water, let's see, let's pick on, well, it doesn't start until this pressure. So let's pick at 300 millimeters of mercury as the equilibrium vapor pressure. For diethyl ether, you get that at this temperature, which to me, maybe 10 degrees Celsius. And for water, you have to jack water up to a temperature of, maybe 75 degrees Celsius. So that's just a way to compare what temperature do you have to get to, okay? So does this seem reasonable that diethyl ether is more volatile? Does that seem like it to you? Yeah. All right. The blue line is benzene, nasty benzene. And benzene, remember, looks like this, where I said basically this is your C6H6. I have to speak that slowly. So there's a carbon at each one of these little corners. It's cyclical. It's alternating single and double bonds, but they kind of resonate to make that cool structure. Okay, and there's a hydrogen poking out from each carbon. That's benzene. Benzene is generally nonpolar. Okay, and you can kind of see that benzene's a little bit, it's between the two, the water and the diethyl ether. Then we get to toluene. And toluene is benzene that has one of its hydrogens substituted. Okay, so instead of having a hydrogen here like benzene, it has, we call this CH3 a methyl group. It has a cute little methyl group on the ring. Okay, so that's toluene. Notice that, what do you think? It's a little less volatile? Kind of, we said water was less volatile than diethyl ether, so kind of as we're going this, we're decreasing volatility. What do you think? We kind of, comparing these structures, we kind of get a little more induced dipole going on, a little more polarizability with size. And then last but not least, we have another red line, which is aniline. And aniline is also benzene with a substitution, but it's substituted with, is it ammonia? I should know this. But an NH2 group. Aniline, that's the word. It's aniline. Starts with the letter A. Can't remember what that functional group is. But it's even less volatile. Stronger intermolecular bonds. Thank you, amine. Amine. It's like, very good. Yeah. So this, again, and we'll be seeing this later in kind of a, it looks like a Y shape when you consider the solids, a phase diagram. But these are liquids, okay, and these are gases on either side of that line. Each individual line, I'm just kind of showing you. Okay. All right. So I mentioned that this is just actually, these numbers were on the previous chart. They're just kind of zooming in on a handful of temperatures, what the equilibrium vapor pressure of water is. Okay. So I mentioned this room, okay, if you think room temperature is about 24, then we thought 30 millimeters of mercury would be kind of the saturation pressure of water vapor. Works for me. Okay. So we got a couple problems to work and then a problem slide. Wait, yeah, an assignment slide. So I went ahead and printed off the problem so I could kind of have it as we're working it. But to draw what's going on, oops, it looks like this. You know how I like to draw a picture, take some time. I think what works well is a big Erlenmeyer flask for these things. Okay, so here's my big Erlenmeyer flask. We have a couple, and I'm going to go ahead and stopper it. We have a couple of problems where basically you have a residue of liquid down here. That's my puddle or my residue of liquid. Okay, in this case it's H2O, water. Okay. It says that 0.110 grams of liquid water, that's my puddle down here, is placed, and it goes ahead and gives me the volume of the flask. So I'm going to put that mass next to the liquid water. 0.110 grams of water, and then I'm going to go ahead and say V is equal to 5.35 liters. Cool. They give me a temperature. Thank goodness. I'm going to give you a hint. This, I'm going to go ahead and start to draw my water. Those black particles are my water vapor. Go ahead and show my water vapor. Some of that liquid's going to go ahead and fill that, break its bonds and form a gas. Okay, and it's going to be in dynamic equilibrium. We're setting ourselves up to use the gas law equation. PV is equal to nRT on this gas, this water vapor. So remember when we used that before, kind of take the dust and get the dust off of that equation. PV is equal to nRT. You can probably see it on the next slide. We need to find, we can only have one unknown. So do you guys, let's go ahead and finish this thought. So every problem is a little bit different. It gives us the temperature. T is equal to 25 degrees Celsius. Remember, and I'm going to remind you now, you can't use that temperature directly. We need to get to Kelvin. We can do that by adding 273.15. So the question at hand is, that's kind of showing you what the problem is. The question is, we're supposed to verify, and actually that's a hint. Verify because they're suggesting that all of the water will evaporate. All of the water will evaporate. The reason that's an issue is it must be bumping up. It doesn't bump into the saturation equilibrium vapor pressure. If this becomes saturated, this stops evaporating. So they're saying it's all going to evaporate. So you're going to be underneath the saturation amount at that given temperature. What is the saturation amount at that given temperature? We'll look at a table. Okay, so that's kind of the problem we have going on. So the temperature was 25. So this is our target water vapor pressure, 23.76. It can't go higher than 23.76 at that temperature because it would be in equilibrium. All right, so actually there are two ways to approach this type of problem, and one makes more sense than the other. Okay? The first is to assume that the first is actually what we're going to use to work this problem. We're going to assume that that 0.110 grams of water is all going to go ahead and evaporate. And in that case, given that volume and that temperature, we're going to use the ideal gas law equation to come up with the partial pressure, and we're going to compare it to the table pressure. And if our pressure, after all that water evaporates, is underneath the saturation pressure, we're going to go, dude, it all evaporates. You're fine. Okay? Alternatively, so that's the one we're going to use. Alternatively, given that volume and that temperature, we could say, well, what pressure of, oh yeah, given that volume and that temperature and what the saturation equilibrium vapor pressure would be, okay, we could go ahead and backtrack and say, well, what mass of water is that? And we could compare that mass to the 0.110 grams, okay? And if that mass, let's see, how's this work? If that mass was greater than the 0.110 grams, then it's all going to evaporate. If that amount is less than the 0.110 grams, then you're going to have liquid left over, and it's not going to all evaporate. So those are, broadly speaking, two ways to approach that. So since they said verify that that entire amount, the 0.110 grams, is going to evaporate, we're definitely, and they asked for the partial pressure, because it's going to be under the saturation pressure, we're going to take the first approach. So like I said, I'm a little bit apologetic, but Unit 5 and Gen Chem 1 was gases. So go ahead and remember how we did all that. And a lot of times in your high school experiences, you were exposed to gas law problems. Okay. So if a gas is behaving ideally, then its pressure times its volume is equal to its number of moles that's banging around at that pressure and get that given volume times ideal gas law times the temperature it's occurring in. In this case, we know everything except for the pressure. Okay. Remember, we're going to get N by mass of the water. So let's knock out N first. Let's take that mass of water, that 0.110 grams, and I'm still going to, on your test, look for you to show me working out the molecular, or the molar mass, the molar mass of water, but it's 18.02 grams per mole. Definitely got to be factor label. No ifs and ands and buts about that. The grams will cancel. We'll be left with N, the number of moles of water. Got to remember everything we did in Gen Chem 1, rounding correctly. So we have 3 significant figures in the mass, and so that's why we're rounding to 3 significant figures in the moles. We have 4 here, okay, 1, 2, 3. So that's our N. So that's going to go right there. Okay, so we have a set of everything except pressure. So our N we got from the mass. The temperature, we better go ahead and convert it to Kelvin, because we just got to, absolute temperature scale. And the volume was given, 5.35 liters. Now ready to plug and chug, making sure that we include units with everything. So P is equal to 0.00610 moles times 0.082058 liters atmospheres per mole Kelvin, also in the numerator times 298 Kelvin, all divided by 5.35 liters. So units that cancel, we got moles canceling, we got, I love canceling stuff, Kelvin canceling. We have liters in the numerator canceling with liters in the denominator. So we're left with units of atmospheres. How many significant figures we need to round to? Yep. I see 3 fingers. Very good. So the partial pressure of your water, if it all evaporates, okay, is going to be 0.0279 atmospheres. But we can't compare that directly with the table yet, because if you look at the table is in millimeters of mercury, and this is in atmospheres. I don't know if you guys remember, there's a relationship of 760. So it's 1 atmosphere is exactly equal to 760 millimeters of mercury. So we're going to go ahead and make that conversion. Take the 0.0279 atmospheres times 760 millimeters per 1 atmosphere, and that's exact.
How are you?
So now we have a millimeters of mercury to compare to the millimeters of mercury on the table. All right. So if you look back, compare the 23.8 milligrams of mercury, that's saturated water vapor at 25 degrees Celsius, and this comes in under that. So this does, as the problem suggests, verify that it's all going to evaporate when you're still under saturation. Any questions? Andrew, borrow your textbook for a minute.
Sure.
Thanks. So I think for that 477, you're going to want to draw a line through it and put 513. Thank you. And table 12.4. That just didn't make the changes. Let's see. Right here, in case you need it, and you will for your homework. 513 and table 12.4. Thank you. Alrighty. Whew, that's a lot of work. Yeah. What doesn't kill us makes us stronger. New problem. New problem. Let's go ahead and draw another Erlenmeyer flask and see what we got going on with this. Again, we have a sludge of liquid at the bottom. So some of the details have changed though. Here's my Erlenmeyer flask. I'm going to go ahead and stopper it. And I have a puddle of liquid water down here. And it's going to evaporate to a certain extent. Notice that my puddle has a mass of 1.25 grams of water, liquid water. My volume of my flask is 9.70 liters. The temperature is given, it's a little higher than it was before, so water will have a higher equilibrium vapor pressure, won't it? So with two significant figures, because there's a decimal there, degrees Celsius is the temperature given. Okay. So clearly it's different because it says verify under these conditions that not all of the water will evaporate. So basically that liquid water is going to go into the flask, become a gas, and it's going to bump up against the saturation equilibrium vapor pressure. So not all of it's going to evaporate. Okay? So take that into consideration. Then the two things we're supposed to do are we're supposed to come up with the partial pressure of water. And see, to me, that's from the table. As long as it's saturated, you can actually knock that out from the table. Does that make sense? Okay, at that temperature. But this has a little bit more of a calculation. We're supposed to come up with a residue of water that stays liquid. Okay, calculate the mass of water that did not evaporate. Remains liquid. Alrighty then. Let's see. We got volume, we got temperature. I think in this case we're going to go with the equilibrium vapor pressure of water at 40 degrees from the table. And we're going to solve for N. So let me go ahead and say that up here. We're going to use P is equal to the EVP at that temperature. This is actually strategy 2. EVP at 40 degrees. Okay, and then we're going to solve for N. Solve for the number of moles. Are we the only ones working here? Maybe. Okay. So 40, you're like, dang, 40? Actually, I have a better table, but you're like, this doesn't quite make it. And actually, we could do a little bit of estimating on your homework. I'm somewhat apologetic. You're going to kind of have to do some estimating. I hated the whole log tables when you had to get something between the two numbers. It just drives me nuts. So just kind of do your best to estimate when that comes, okay? So what we want is in between there at 40 degrees Celsius. We could use this one, okay? I know this is kind of a busy one, but just to kind of remind you how this works, we could pick 40, okay? And we could go up on the black line and see, you know, you guys have had to do some of that to estimate what this equilibrium vapor pressure of water is at that temperature. But instead of that, okay, I have a better table for you coming up. This strategy, these two possibilities are the same as the last problem we worked. Okay? Only the mass has changed. Instead of 0.110 grams, we were given 1.25 grams of water. Our first approach would be to calculate what the partial pressure of water would be if that liquid entirely went to its gaseous state. And there's a good chance what we would find out is that would be a higher pressure than the equilibrium vapor pressure, okay? But instead, actually, this other one makes sense. And this other one makes more sense because we're going to be able to find that tipping point, the mass of water that does go from being a liquid to being a gas. So this other one says, go ahead, look up, I know this is 35, it should say 40, because that was the temperature. So we're going to look up the equilibrium vapor pressure of at 40. Okay, we're going to look it up at 40, and then we're going to use that as our pressure in PV equals nRT. Okay, and we're going to backtrack and find number of moles. What we're going to find out is that this mass is going to be less than your 1.25. So you're going to have some residue. Since this problem asks us to calculate the mass of the water left as a liquid, the mass of the water that did not evaporate, the second one makes more sense. Okie dokie. Ideal gas law equation. Now remember, I have to concentrate, and you probably do too, to get N by itself, because we're after the number of moles and then ultimately mass of water vapor that can be held at that pressure, volume, and temperature. We divide both sides by RT. Okay? So here's I didn't catch the earlier one, but I caught this one. You went ahead and corrected where do you find that table. And it's instead of the 477, it is on page 513. Instead of being labeled 12.2, it's going to be 12.4. But when you go to that, and like I said, you're going to want to do that for your homework, you're going to find that pick off the equilibrium vapor pressure of 55.3 millimeters of mercury. So we're going to use that as our pressure in our PV equals nRT. But we can't use that directly, can we? Unless we use a different R value, which some people do. But using the R value that we use, we better convert it to units of atmospheres. So 55.3 millimeters mercury times 1 atmosphere per 760 millimeters mercury. Rounding it to 3 sig figs. So that is the pressure we're going to plug into our ideal gas law. Okay, getting ready to plug and chug, plug and chug. Okay, so we already got the pressure the way we need to. Of course, we need to kick those that temperature from Celsius to Kelvin by adding 273. The volume's ready to go, 9.70 liters. So plugging in, it looks like this, where N is equal to 0.0728 atmospheres times 9.70 liters. Those are in the numerator, all divided by 0.082058 liters atmospheres per mole Kelvin. Also in the denominator is the temperature, 313 Kelvin. So unit-wise, we gotta cancel. Okay, so atmospheres, cancel, liters, cancel. And here, all we're left with is some terms in the denominator. So kelvins cancel in the denominator. Okay. Then we have units of moles in the denominator, which makes it moles in the numerator. Okay, round it to 3 sig figs. So the moles of water that will evaporate at that temperature based upon the equilibrium vapor pressure is 0.0275 moles. Does this make sense? The next thing you're going to see is to get that into grams. Maybe. It doesn't want to work anymore either. Okay. So using the molar mass of water, we take the moles that we came up with, the 0.0275 moles times 18.02 grams per 1 mole to get a mass of 0.495 grams. It's tired. Okay, so, you know, the coup de grace or whatever, the last thing we need to do is to say, so if that's the mass of water that gets into its vapor phase, based upon the liquid that we had to start with, which is 1.25 grams, can you see the liquid remaining is 0.75 grams? And that's the answer. What's the answer to the first question? What is the equilibrium vapor pressure of water? All right, if I can find them. Actually, to tell on myself, I thought we'd get. I would have signed the first one, problem 30. Wednesday. So I had it ready to go. And since then I've had night class and there you are. Okay. Oh, nope, that wasn't it. Trent. These are the ones that you already did. You just handed these in. Oh, 29. I said 30, but it's 29. Okay, so here's hints for that first one. So the first one has to do with bromine. I know that it says bromine is established between bromine liquid and bromine gas. Okay, so I kind of have it drawn there. It gives you the temperature, it gives you the volume of the container, and it says that the vapor, so that's gas, right, weighs 0.486 grams, and it wants to know what the pressure is at that temperature. You know, so you probably already have an idea, but I'll kind of show you what I had. So the ideal gas law equation, you have those 4 variables. I a lot of times just write them down and see what I don't have. Okay, so the temperature is given, the volume's given, the number of moles, we can use the mass of vapor, okay? And so the only thing we're missing is P. Okay, so we can rearrange PV equals nRT, P by itself, and plug in everything else. It's a good one to kind of get you thinking. Okay, so the next ones would be ones I got ready today. Be right here. Okay, so in this one, different substance, acetone, another volatile substance. And notice if you read it a few times, it gives you the formula for acetone, which you're going to need. Let's see. Acetone looks like, gosh, it's been so long. Basically, it has a middle carbon, and it has 2 methyl groups on each side. Oops. And it has a double bond O. Very symmetrical. Acetone. So it tells you, the thing it gives you actually is a physical property. It gives you the density of the vapor when it's in its equilibrium phase. So I drew some liquid there, and I drew the particles, those are the gas particles there, and equilibrium is established. So that gas is running 0.876 grams for every liter you got. So we've done this before in Chem 1. You go ahead and set as your basis 1.00 liters. The reason being that now you know the mass, okay? Basically lifting that off the physical property. Okay, so you somewhat arbitrarily set that volume. So now you have a volume, now you have a mass is 0.876 grams of vapor, acetone vapor. The temperature was given, and you're supposed to again knock out the pressure. Notice, and I didn't put it here, but a little twist, it says they don't want the pressure in atmospheres, which is what you're going to get it in. You need to look up the relationship between atmospheres and kilopascals. You can do that, right? Better you than me. Oh, go back. The next one. Oh, really? Is I'm almost running out of patience here. I need to click this button. Okay. So let's see, we did this one, okay, 33, okay. So the next one, notice I went ahead and brought in that famous table 12.4 from your textbook. So if you read it a few times, it's about water and pressure cooker. So basically it says that if your pressure cooker is set to max out or set to run at 2 atmospheres, what's the boiling point temperature of water at 2 atmospheres? Okay, so basically you need to first convert, since this table is millimeters of mercury, first you got to go from those 2 atmospheres to millimeters of mercury. Okay, and then you need to find that millimeters of mercury on this chart, and I'll give you a hint, it's down here, and also give you a hint, just do your best. Okay, because it's kind of not really obvious. But you take the pressure and you find the corresponding boiling point temperature. The next one's similar. Oh, really? Oh. The next one's similar. You'll need that same table. But again, just kind of do your best. Okay. A couple of questions. I'll post these hints. You need to estimate. And the other 2 are back to, or is there 2 or 1? Oh, I ran out of time for 36. So 35 looks something like this. Like, really? I didn't have time to put the stops in it. But it's a classic where you have a carrier gas that's the helium, and you're bubbling the carrier gas through aniline, which is a volatile liquid. Okay? If you read the problem, it will describe basically the carrier gas is going to pick up some aniline, and it's going to be stored over here. One of the things I didn't emphasize, because it took me a little while to work the problems, is that the full volume, 25.0 liters of helium, will end up 25.0 liters of helium with aniline. Okay, so that volume stays the same. they tell you that that liquid aniline, that mass of the liquid starts at 6.220 and ends at 6.108. You can get the mass of the aniline that went into, it got carried away as a gas, okay? So then over here, you do have a mixture, but both the helium and the aniline share that volume. They both share that temperature. You can get the number of moles of aniline from the mass that went away, and you can solve for pressure. The last one, I will jot something down on how much, and I'll push it out there, okay, for what it's worth. Okay? Have a great weekend.